Hello to all of you. In the previous lecture, we gave you an idea about the contents of the syllabus of this CFD course. And also, we talked about the major references that we use to study this course if you want. And we talked about, or we defined the CFD technique, and also have some examples of the application of CFD techniques, and we talked about the main elements of the CFD code. Then we solved example, and we have a review of the type of fluid assumptions and also the types of fluid motion. Then we mentioned the general transport equation of fluid flow and how many terms does it include. Then we solved two examples and we ended the last lecture with unsolved examples. Today we will continue with the second lecture, and in this lecture we will start with chapter 2. This chapter 2 will be covered by two parts or two lectures. The first lecture we will study, will give you an introduction to this chapter. It is steady-state diffusion. Then we will study the one-dimensional steady-state diffusion, which include the grid generation item, and then we will study the discretization method, which include the diffusion coefficient and the gradient flux, and also the source term and how to deal with such parameters. Then we will study the solution of discretized equations, which is TDMA. At this point, we will end lecture 1 of this chapter. Then in the next lecture, we will continue the other part of steady-state diffusion, which we will cover the two-dimensional steady-state diffusion problem, and we will solve another example as we give it the name example 4, because we have solved 3 examples for the one-dimensional steady-state diffusion today. And also we will continue to the 3-dimensional steady-state diffusion. As you see, all the black written text, we will cover the Cartesian coordinates, and the red one, and that item we will study in the next lecture. It will be focused on the polar coordinate system, which is the one-dimensional steady-state diffusion, and we will give you a homework also. Then we will end this second lecture with the spherical coordinate system, which is one-dimensional steady-state diffusion. As we mentioned in the previous chapter, that there is a fourth type of coordinate system, which is the body-fitted coordinate, and it is a more advanced topic that we haven't enough time to cover. Okay, so we will start the introduction to steady-state diffusion. As we see, and we talked about the previous chapter, there is a general transport equation which is a differential equation that covers that controls the phenomena of transport property. So when we say steady state diffusion, that means the transient term will be deleted because partial phi to partial time will be equals to 0. And also there is no convection terms in equation, the general transport equation. So the second term also will be deleted, which is partial rho multiplied by u vector and phi. So the only thing will be left, it's the divergent of gamma multiplied by gradient of phi, which is the diffusion term, and the source term plus the source term S of sub phi will be equals to 0. This is the general governing equation of the steady state diffusion, which is equation 2.1. So if we integrate this equation along the control volume for each cell, it will give us equation 2.2. And as you see, this equation or differential equation, it is more complicated to be understood by any students, and therefore we will leave it at the moment, and we will use the regular form of differential equation, and we will solve many examples. So let's start with this topic, one-dimensional steady-state diffusion with the Cartesian coordinate. Consider the steady-state diffusion of property phi as given for one-dimension domain as shown in figure 2.1. The governing equation is written in equation 2 as shown in equation 2.3, d by dx for the term gamma d phi by dx plus the source term. So as we see, gamma represents the diffusion coefficient, and if we are studying the distribution of temperature, so gamma will be the thermal conductivity, and the source term, it depends on the situation of the problem. Phi sub A and sub B, it is the boundary condition. It's maybe for the temperature at the left side, TA, or TB are on the right side. So if we take a close look at the figure 2.1, we will see that there's a control volume which is centered at point P, and at the left side it is centered with point big W, and each side centered or big A. So when we start our numerical solution for this the problem, we will start with the grid generation. So this grid generation will be divide the domain between point A and point B into a number of control volumes, which is shown in the figure 2.1. We start our solution by grid generation, which is dividing the domain between point A and B into a number of control volumes. This is point A and this is point B, dividing the domain between these 2 points into a number of control volumes. Each control volume, this is the control volume, each control volume have a one nodal point at its center, which is represented by a letter P, capital letter P. And there is 2 points at the neighboring, 2 control volumes neighboring this control volume. The one on the left side, this one, it is represented by a center point which is called capital letter west or W, and the other on the right, this one, it is represented by a central point which is east or capital letter E. This phase is represented, or it is called the interface between the neighboring control volumes, is represented by a small letter W. And the other face, this one, on the right side, it is represented by a small letter E, small letter, which represent the interface between the neighboring control volume, which is the one we are talking about, and the control volume on the right side, which is the east control volume. And the distance between the capital letter W, which is the center of the left control volume, and the point P, it is delta X, big W and big P. And the distance between the point P and this point, which is the east central point of the control volume on the right, it is delta X, big P and big E. The distance between the left interface, small w, and big P, it is delta X, small w, big P, and the same goes for the distance between the big P and the small e, which is delta X, big P, small e. Since this point is at the center, that means this distance delta X, small w, big P, equals delta X, big P, small east. And the distance delta X, big W, big P, equals the distance delta X, big P, big E, because we said that all of the control volume have a central point. So that means this distance equals this distance, and also this distance equals this distance. Therefore, the distance between delta X between each node, it is delta X as shown here. Then we will start the discretization technique, which is the integration of equation of the last governing equation, which is we integrate equation 2, 3 from the west side of the control volume to the east side. So it will be integral from west to east, d by dx, gamma d phi by dx, and multiplied by the control the volume of the control volume, dv, plus integral from west to east, source term multiplied by the volume of the control volume, which equals 0. Substitute, since dv equals to cross-sectional area, which is a, represented by a, multiplied by dx, substitute this dv into this equation. It will give us equation 2, 4, which is, when we open the integral, it will be gamma multiplied by a d phi by dx for the east side, minus the same goes for the west side, plus the average source multiplied by delta v, because the source term is independent of the control volume distance. So A, it represents the cross-sectional area of the control volume, delta V is the volume of the control volume, and the average value of the source term S is represented by a letter S bar. So in order to continue the discretization process of equation 2, 4, we have to have value for gamma at the east side, and also gamma at the west side, and also d phi by dx, the gradient of phi in the east side in the interface at the east, and also d phi, or the gradient of d phi of phi, which is d phi by dx at the west side. And also we have to know how much value of this s bar multiplied by delta v. So when we take a close look at figure 2.2, we have to know exactly how much value of gamma at the west side and gamma at the east side, and also the gradient of phi at this point and the gradient of phi at the west interface, and also how much is the value of s bar multiplied by delta v. As we know, our solution will be ended with the values of the distribution of phi at all big letters, which is phi at big W and phi at big P and phi at big E. And therefore there is no such value of phi's at small letter. Therefore we have to solve this problem. And also we don't have the gradient of phi at the east interface or the west interface. So to know such value, we will study the method of evaluating the diffusion coefficient value. Generally, there are three common methods to calculate this gamma value. For instance, if we want to calculate gamma at west, either we used the most common method, which is the arithmetic mean method, or we use other method like the harmonic mean or the geometric mean. The arithmetic mean method, it's the average value of the gamma value of the neighboring points for the west interface. That means we calculate gamma at west side, add gamma at the point, and we divide the sum by 2. That means we take the average value of the neighboring values of the at the point. This goes also for gamma at east. We add the values of the neighboring points, gamma at P plus gamma at big E, divide the summation by 2. The other method, it's the harmonic mean, and as shown, if we want to calculate gamma at west interface, we used this formula to calculate it. We multiply both values of the neighboring points by 2, and divide this value, divide the result by the summation of these values, which is gamma at west point plus gamma at the big point P. And also for the gamma at east, if we use the harmonic mean, we multiplied the neighboring values at point P and point east by 2, and we divide the result by the summation of its value, gamma at big P plus gamma at big E. The geometric mean method, we multiplied both values and take the square root. So if we want to calculate gamma at west interface, we multiply both neighboring points, gamma at big W multiplied by gamma at big B, and take the square root of the result. And same goes for the gamma at east interface. We multiply the neighboring values, gamma big B multiplied by gamma big E, and we take the square root of its result. So in general, if we have a function, suppose the gamma value is constant at all the domain, so no need to use any of these methods. And if the gamma values change with any variable, with the position or with the temperature, say you have you are studying the temperature distribution, and the thermal conductivity is gamma, and this thermal conductivity is a function of temperature. That means at each point there will be a solution of T. So therefore the value of thermal conductivity will change according to the location of this point. So there will be a distribution of K in the domain. So therefore we will use one of these methods to calculate K at each point. So the most common method, it is the arithmetic mean method to calculate the distribution of gamma. So we use equation 2,5a and b to calculate gamma at west interface and east interface. Now we will talk how we calculate the value of the flux d phi by dx. As we said before, that since the value of phi are defined at only the big letters, capital letters, which is the nodal points, we have to implement an approximate method to calculate such value. An approximate distribution of properties between nodal points will be used. Therefore, gradient values and hence fluxes and the control volume phases are approximated linearly. That means we will use a linear approximation, which is either forward difference or backward difference or central difference. These three methods are adopted, or these three approximation methods are adopted. And the accuracy of these methods will be different from one to another. So these approximation method is shown in Appendix A. In general, in a uniform grid, the central difference scheme is the most accurate method between the three methods, and it is shown in equation 2,6 and 2,7, and that means gamma multiplied by A multiplied by d phi by dx at the east side will be equal to gamma at east, area at east, and multiplied by phi at big E minus phi at big P divided by the distance in between the two capital letter points P and E. And also gamma A d phi by dx at the west interface will be equal to gamma at west interface, area at the west interface multiplied by the value phi at big P minus phi at big W divided by the distance between the two capital letter points WP. That means this gradient at the east side will be equal to this value if we use the central difference method. Okay. So let's move to the appendix A, and we will study how we use each three schemes. Let's start with the forward difference scheme. Consider a one-dimensional function phi of x, which is given in figure A1. The distribution of phi, suppose it is known. This distribution with a uniform grid of equal space delta x, as shown in figure A1. And the control volume, it is shown in the notation. Its notation is shown in figure A2. If we use the Taylor series of expansion of phi at x plus delta x around point I, at x is given as phi, as is shown in equation A1, phi at x plus delta x equals phi at x plus the first derivative of phi at x multiplied by delta x plus the second derivative of phi at x multiplied by half of delta x squared plus etc. The notation, if we replace the notation of phi at x with the phi at p, big P, and also the notation of phi at x plus dx with the notation of phi at big E, as shown in figure A2. Equation A1 will be written as phi at big E equals phi at big P plus the first derivative of phi at big P multiplied by dx plus the second derivative of phi at P multiplied half of dx squared. Rearranging equation A2 yields, if we take this term, if we take this term on the left side and the others to the right side, and we will this equation A2 will be as shown in this form. So the first derivative of phi at P multiplied by dx will be equal to phi at east point minus phi at big P minus the second derivative of phi at P multiplied by half the value of delta x squared minus etc. If we divide this equation by delta x, we get the equation A3, which is the first derivative of phi at point equals phi at east point minus phi at big P divided by delta x minus the second derivative of phi at P multiplied by half the value of delta x minus etc. As we see, if we refine the value of delta x and make it smaller, or in other terms, if we increase the number of the nodal points in the domain, that means we are refining the grid. So the smaller the value of delta x, the smaller the value will be delta x squared, and that will lead us to this term will be approximately 0. So this is the most major source of error of this method. Therefore, approximately the first derivative of phi at point P will be equal to phi at east point minus phi at big point divided by delta x as shown in figure A4. So the error in equation A4 can be reduced by decreasing the value of delta x further. In general, the truncation terms of the finite difference scheme contain the value of delta x to the power n, and the power n of delta x specify the rate at which the error approaches 0 when the grid is refined. The power n is defined as the order of difference approximation. Therefore, equation A4 is said to be a first order in delta x, and it can be written as shown in equation A5, and it is d partial phi to partial x, or the first derivative of phi at point P, equals phi at big E minus phi at big P divided by delta x plus the order of delta x. Since point E is downstream point P and x at east point is greater than x at the point big P, and it use property value at phi east and phi point, therefore equation A5 is called the forward difference scheme with respect to point P. So this equation A5, we are calculating the first derivative of phi at point P, and we are only using the phi at this point big P and the phi at the point next to it or forward to it, which is phi at big E. Therefore, it is called forward difference scheme. The backward difference scheme, we use also the Taylor series expansion of phi at x minus delta x around point I at x, which will be given as equation A6. That means phi at x minus delta x equals to phi at x minus the first derivative of phi at x multiplied by delta x plus the second derivative of phi at x multiplied by half the value of delta x squared plus etc. The notation x is replaced with the notation big P, and therefore the phi at x will be replaced with the phi at big P, and also the phi at x minus dx will be replaced with the value of phi at big W, as shown in figure A2. Therefore, equation A6 will be written as phi at west point minus equals phi at P, big P, minus the first derivative of phi at big P multiplied by delta x plus the second derivative of phi at big P multiplied by half the value of delta x squared plus etc. If we rearrange this equation, and we will take this term and write it to the left side, and the other terms we will write it to the right side. It will be this equation, which is the first derivative of phi at big P multiplied by delta x equals phi at point minus phi at west point plus the second derivative of phi at big P multiplied by half the value of delta x squared plus etc. If we divide this equation by delta x, we will have a value of the first of we will have equation A8, which is the first derivative of phi at point P equals phi at point P minus phi at point west divided by delta x plus the second derivative of phi at p multiplied by half the value of delta x minus etc. Again, this equation A8 is said to be first order in delta x, since point W is upstream of point P and x of west point is less than x at P, and it uses property value at only point P and point west. Therefore, equation A8 is called backward difference scheme with respect to point P. Therefore, the gradient of phi at big P, if we use this backward difference, we will use only the phi at big P, and the phi at the west or at the upstream value, which is phi at west, as shown in equation A9. The third method, it is the central difference scheme. By subtracting equation A6 from A1, we have equation A10 as shown. Phi at x plus delta x minus phi at x minus delta x will be equal to 2 multiplied by d phi by dx at x multiplied by delta x plus the third derivative of phi at x multiplied by delta x to the power 3 multiplied by the factorial of 3 plus etc. Okay, so if we change the notation as shown in figure A2 and rearranging the terms, we will result the equation A11, which is the first derivative of phi at point P. It will be equal to phi at east minus phi at west divided by 2 multiplied by delta x plus the order of delta x to the square power. The gradient is at midpoint P between point west and point E. Therefore, it is called the central difference scheme. So equation A11 shows that the accuracy of this scheme is a second order in delta x, and it means that that refinement of grid will reduce the error more quickly and rapidly than in the first order schemes. In finite volume discretization, the gradient at face E is estimated as follows. So equation A11, we find the gradient of phi at point P, but as we said before, we want the gradient of phi at the interfaces. So equation A12, it will calculate the gradient of phi at east interface, which will equals the phi at east minus the phi at point divided by the distance, which is delta x, which is double the distance between the two neighboring points. So as a homework, use the Taylor homework number 1, use the Taylor series to find the value of the gradient of phi at the west interface and prove it equal the value of phi point minus phi at west point divided by delta x. There's a fourth type of scheme, which is the quick difference scheme, and it needs more than 3 points to calculate this the value of gradient at each interface. So if we use the Taylor series expansion to calculate the value of at phi at the interface east, we will use equation A13 phi at big E equals phi at the interface east, small east, plus half the value of delta x multiplied the first derivative of phi at east interface, plus half multiplied by half delta x to the power 2 multiplied by the second derivative of phi at east interface plus the order of delta x to the cube to the third power. And the same goes for phi at point as shown in equation A14, and phi at big W is calculated as shown in equation A15. If we multiply equation A13 by 3 over 8, it will lead us to equation A16, and if we multiply equation A14 by 6 over 8, we will have equation A17, and if we multiply equation A15 by minus 1 over 8, it will lead us to equation A18. If we sum all the three resulting equations, which is A16 plus A17 plus equation A18, it will give us equation A19, which is phi at the interface E plus the order of magnitude delta x to the power 3. It will be equal to 3 over 8 phi at east plus 6 over 8 phi at point minus 1 over 8 phi at big W. Therefore, the accuracy of the quick skim for the convective flux, because this skim is it's always used for the convective diffusion problems. Therefore, we will not use it in this chapter. Anyhow, the accuracy of this skim for the convective flux at the midpoint cell faces is in a uniform grid of equal space delta x is a third order in delta x. Hence, the value of phi east at the face east, it will be estimated as shown in figure A20. As a homework, you try to calculate phi at the west interface and prove it to be equal to this equation. As you see, if we want to calculate phi at east interface, we will need 3 points to be known, and that is phi at east, phi at point, and phi at big W. And if we want to calculate phi at west interface, we need phi at west point and phi at P and phi at west. Therefore, it is this scheme is a higher order scheme. Let's go back to our third parameter, which is the source term, and how we calculate this term and the differential equation. If we assume that this source term is a linear function of the dependent variable phi, we will have this equation 2,8, which is S bar multiplied by delta V, it will be equal to a constant value SU plus the slope of the function SP multiplied by the dependent variable phi at point. If we substitute equation 2,6 and 2,7 and 2,8 into equation 2,4, it will give us equation 2,9. As shown in this equation, there is 4 phi point values, 3 phi point values. If we arrange these values and put it on the left side, all sharing this parameter 5 point, and the others will put it on the right side of equation 210. Hence, the discretization or the general discretization form of equation 210 will be shown as in equation 211. That means this term we will name it A point, and this term is A west, and this term A east, and A SU will remain as it is. This equation 211 it is the general discretization form, and it have a constant values A point, A west, and A east, and these parameters is shown in this table. So A west, it will be equal to gamma west divided by delta x WP multiplied by A west, and the same goes for A east. And A point, it will be the summation of A east plus A west minus SP. So we will have a set of equation which is equal to the number of the control volume in the domain, and each equation will be, algebraic equation will be different from the other. So if we divide our domain into 5 points, and that means we will have 5 algebraic equation with 5 variables. In order to calculate these variables, we will need a technique which is called the TDMA method. It's the tridiagonal matrix solver. So in this method, we will write the equation, and we will put it in a matrix form, and we will solve it. If you are a student in a classroom, you will not need to you will not use this method in the classroom and make a program and put it in your computer. This method will only be needed if you make a research and you have to make a program with the Fortran language or MATLAB, and then especially Fortran or Cook Basic, and then you will have to know how it is written. So you can study this method by watching these slides. As you see, we used here the forward elimination technique, and then we will use the back substitution in order to reach our final destination, which is the solution of phi at each nodal point. So if you are in the classroom, you can use your scientific calculator and use it to calculate, to type all the algebraic equation, and you can find easily the solution you need. Let's take a few examples about the one-dimensional steady-state diffusion problem. The general one-dimensional steady-state heat conduction equation, if we want to study the energy equation with the dependent variable phi is replaced by T, we will have equation 212, and it is written as d by dx equal to k dt by dx plus the short term equal 0. So we replaced the gamma with the thermal conductivity value, and the phi with the temperature, which is the dependent variable, and the source term, it depends, maybe there is a heat generation source term or sink term, and etc. Example 2.1. Consider a problem of a source free heat conduction in an insulated rod, or maybe it's a wall or slab, and this rod, insulated rod, whose ends are maintained at a constant temperature values of 100 to the left and 500 to the right, 500 centigrade to the right respectively, as shown in figure 2.3. The one-dimensional energy equation is given as equation 2.13, d by dx, k dt by dx equal to 0. There is no source term. It is required to write the system of linear algebraic equations into a matrix assembly form, then calculate the temperature distribution in this rod using the finite volume method, knowing that the thermal conductivity value is 1000 watt per meter Kelvin, and the cross-sectional area have the value as shown in this slide. We will always start the solution by dividing our grid of the domain of length L into a number of control volumes, and we will divide it here to 5 control volumes equally spaced, and as shown in the figure 2.4. So therefore delta x equals to L over N. It will be 0.1 meter. We will start the discretization technique with the internal nodes, which is these internal nodes, which is 2 and 3 and 4. These all together represent the internal control volumes, and which share the same algebraic equations with a different value of A west or A east, whatever it is. So we will apply equation 2.10, which is with no source term. We will integrate the general differential equation, and we continue the same procedure until we reach equation 2.14, which is K east. It's the same as this equation. Therefore, this equation 2.14, it is K east at delta x point east multiplied by A east. This is represent A point, T point equals A west, T west plus A east, T east. There is a notation that this term have to be equal to one of these, and this A east has to equals the other term, which is A east, and A east and A west are equal in this question, and it will be equal to big A, and the constant the thermal conductivity is K, which is equal to K east or K west, and delta x equal to delta x at point east equals delta x at west point, and equals to delta x. Therefore, the discretization or the general discretization form of equation 2.14 for all the internal nodes is given as shown in equation 2.15. This red value is added just for the sake of programming, and the parameters of this equation 2.15 will be shown in this table. Therefore, A west, it will be equal to K A over delta X, and A east the same value KA by delta X, and A point will be equal to the summation of A neighboring point minus SP, and there is no SP or SU. Therefore, when we add SU, it's a zero value, therefore it will not change the value of equation 215. Now let's discretize for the nodal point or the control volume number 1, which is at the left side of the domain. So integrating equation 213 along the controlled volume from the east to the west, from the west to the east, sorry, it will give us equation 216, knowing that there is no west temperature, and it will be replaced by the boundary condition TA, and since the west interface is a different distance, half delta X, it will be substituted here half delta X. Rearrange this equation and put all the terms which is multiplied by T point to the left side, and the others put it to the right side, and therefore since there is no T west value, it is replaced with TA. We will put 0 multiplied by T west and write the remaining on the left side. We see a strange shape of a new value. It will be distinguished on equation 217, which is 2Ka over delta X multiplied by the term TA. This value, we will give it to SW, and this value, it is doesn't look like any one of these, since there is here this for the east value, Ka by delta X for the east value, and there is no such a thing here. It will be 0 for T west, and this will goes to the SP, and this plus sign, it is minus minus, so minus multiplied by minus sign will give us to plus sign. That means this term, it is AP. A west is 0, and A east, this A east, and minus SP, it is minus minus SP. So therefore minus SP. SP is negative, so minus the minus is positive. Therefore minus 2Ka over delta X, it is the SP value. Okay, let's delete this. Sorry for my bad English, because I never talk English in my country. Okay, so let's make the discretization technique for control volume number 5, which is at the far east of the control volume of the domain. And now there is no east temperature. We will substitute T at B, which is boundary condition, and the distance, it will be half the distance of delta X. So rearranging this, and we will put all the parameters which is multiplied by TP on the left side, and the rest goes to the right side. Since there is no TE, we'll put it 0 multiplied by T east, and there will be a strange parameter or value, which is 2Ka over delta X multiplied by the boundary condition TB, and this will be SU. And since this will represent the AP, which is 3 terms, 1 A West, this is A West, and there is no A East, 0, and minus SP. SP is negative of 2KA over delta X, negative of this side, so negative of the negative value will be positive. Therefore, let's delete this, sorry. So we will have a third table, and if we assembled the three tables together, we will have this assembly tables for each zone. So the internal node and node number 1 or control volume number 5 all together with values of variables. So the next step, we substitute these variables which is written in this assembly table with the numbers and rewrite all the discretization equation for all the control volume. And since it is 5 control volumes, that means we will have 5 algebraic equation as shown in figure 222 with 5 variables, which is T1, T2, T3, T4, T5. If we rearrange or write this 5 algebraic equation into a matrix form, it will be written as shown in the matrix system 223. If we solve this matrix system using MATLAB or our scientific calculator, we will have this solution, which is this temperature vector, which is shown at the vector 224. As we see here, the matrix, this matrix on the left side, it have a one main diagonal with 2 neighboring diagonals. That means it have 3 diagonals. Therefore it is called a tri-diagonal matrix, and it is we can calculate this easily by the tri-diagonal TDMA method or a direct method which is Gauss elimination. This represents the SW vector, and this is the variable of the dependent, which is temperature vector. As we see in figure 2.5, these black rectangles, it is the solution distributed at each point of our grid. And the terminal values, it is the boundary condition. So since we have 4 control volumes, this is 1, 2, 3, 4, 5, and this one for the B, and this one for the A boundary condition. And therefore we have 5 numerical solution values with 2 boundary condition. If we connect these these black rectangle, it represent the numerical solution, and the terminals, this one and this one, as we said, it is the boundary condition. Let's go back to the general differential equation, which is shown this one. Our problem, this is the differential equation, this one, the differential equation, sorry, and with a 2 boundary condition. Since it's an easy differential equation with 2 boundary condition, we can solve it analytically, and the solution will be, we give you the solution, T exact solution equals to 800 multiplied by x plus 100. So if we substitute any value of fx within this domain, it will be it will give us the temperature, the exact solution of the temperature and if we connect these values, we will have the line as shown here. So the connected line represent the analytical solution, and the black squares it shows the numerical solution, and we see the agreement between the both solution. But if our this curve represent the validation of our numerical technique or finite volume method. But if the governing equation is so hard to be very complex and it cannot be solved with an analytical solution, therefore we have to in order to validate our numerical solution, we have to validate it with a solution which is must be another non-analytical solution, and always it is an experimental technique, and therefore it needs to build a rig and put few thermocouples to measure the temperature, and we will put instead of the linear line of the exact solution, we will put a red or a star with a different color which represent the experimental measurement, and in this method we will validate our numerical technique. And if there is an error or mismatch between both solutions, that means we make mistakes for the numerical solution and we have to correct it. We have another example here, example 2.2, which is a large slab of thickness 2 cm, L equals 2 centimeters, with a constant thermal conductivity K, which is 0.5 watt per meter Kelvin, and an uniform heat generation term Q equals 1000 kilowatt per cubic meter. The faces A and B are at constant temperature of 100 and 200 centigrade respectively. Neglect the temperature gradient in the Y and Z direction. That means it's only a one-dimensional problem, as shown in figure 2.6. The governing equation, it is given in equation 225. It is required to write the same linear algebraic equation and put it in a matrix assembly form, then calculate the temperature distribution in this slab using the finite volume method. As before, we start the solution with dividing the domain given with with a number of control volume. We will use the number 5. So therefore delta x, it will equal to 4 millimeters as shown in figure 2.7. The numbering of this nodal points, it doesn't matter if you start from the left side or heading to the right side as shown in figure 2.7. So we start the discretization of the internal node 2, 3, and 4 control volume. So we integrate the governing equation 225, all the control volume from west to the east, and we continue our solution until we reach equation 229. A east equals A west equals A, and with a constant thermal conductivity K east equals K west equals K, and delta x from P to E equals delta x from west to point equals delta x. Therefore, the discretized form of the general discretization equation for the internal node will be written as shown in equation 230, and and all the constant values A west, A east, and A point, and SP and SU will be given in this table. As we see here, A west equals K over delta x, and A east Ka over delta x. The same goes for A point, the same as before, and SP equals 0, and SU it will equal to this term, and this is ASU. For control volume number 1, which is the boundary condition on the left, we integrate equation 225 along this control volume from the west to the east side. It will give equation 231. And since it's a boundary condition, temperature at the west side and there is no T west, we will replace it by TA, the same as we did in example 1, and the distance, it is half the distance of delta x. Therefore, we have here a new value in the differential equation. It is the source term, and we will assume it is a linear equation with Tp, which have a constant value and a slope value multiplied by T point. We will find that SU, it will be equal to QA delta x plus this value, and this value is predicted from opening equation 232. And we again discretize or integrate equation 225 along the control volume for the control volume number 5, which is at the far east of the domain. And since there is no east value, we will replace it with the boundary condition TB and with a half distance, half delta x between the point and the B surface. Therefore, we will distinguish that SU in this table will be equal to this term and this term. This equal to this with QA delta x, and SP it will be equal to negative of this one multiplied by TP, and therefore the general discretization equation for control volume number 5 will be written in as shown in equation 236, and A west it will be equal to, as shown in this table, it will be equal to Ka over delta x, and there is no A east, it will equal to 0, and the same goes for the same A point equation. And the source term as written here, it will be written TB instead of TA, and SP the same for as before. So if we assemble the three tables here, we will have the general assembly table, which is for 3 zones, and all the parameters here are written as variable. So the next step, we substitute the given data in our example with this table, and we will write each discretization equation for each control volume. And since there we have 5 control volumes, so we have to write 5 algebraic equation, and it will be shown as in equation 237, and you have to rewrite it, and you have to have the same equations. So we will put it in a matrix form as shown in the system 238, and as you see the matrix on the left, it have to be a rectangle matrix with 3 diagonals, 1 main diagonal in the center and 2 neighboring diagonals, upper and lower diagonal, and therefore it is called a tridiagonal matrix. And the temperature vector, which is the dependent variable, and we want to solve it, and the source term vector on the right side. In example 1, the internal node have no values, therefore SU with 0 values. But here, since we have a heat generation term, so therefore the internal nodes have also an SU value. If we solve this matrix using MATLAB or our scientific calculator, we will have the result as shown in figure 2.8, and the black rectangle dots to represent our numerical solution, and the black curve it represent the exact solution when we solve it analytically. The numerical solution is shown in the vector of temperature in equation 239, and the exact solution is shown in this equation. If we want to calculate the error between the both solution, we use this formula here, this equation, and we take the absolute value in order to cancel the negative sign if it disappears. Therefore, we will for 5 nodal points we will have, if we compare both solutions, we will have table 2.1, and as we see the maximum error it appears in node number 1, control volume 1, it is around 2% or approximately 3%. Therefore, it is an acceptable solution. If we refine our gradient and make it more than 5 nodal 1, we will have a more accurate result. The third example here will be different from other two. It will have a different boundary condition. In a circular pin rod, it is a fin with a uniform cross-section area A. The base temperature is at a temperature T base 100 centigrade, and it is perfectly insulated at the other end. So here we have a rod or a fin with a base temperature 100, and the other side is perfectly insulated. That means there is no heat flux. The environment has a temperature of 20 degrees centigrade, and there is a convection heat transfer coefficient between this hot rod and the environment with an convection heat transfer coefficient. So the general heat energy equation is given as shown in equation 240, d by dx, k dt by dx, minus hp multiplied by t minus t infinite equals 0. H represents the convective heat transfer coefficient, p represents the fin parameter, and k for the thermal conductivity of the fin material. It is required to write the system of algebraic equations into a matrix assembly form, then calculate the temperature distribution along this fin using the finite volume method, and compare this numerical solution with the analytical solution that is given in equation 241. Knowing that the m value here, it is given as m square equal to hp over ka, which is equal to 25, and the L is 1 meter, the length of the domain, it is 1 meter, and also we have the x is the distance along the fin. As usual, we start our solution by dividing our domain into a number of control volumes. Here we choose 5 control volumes, therefore delta x will be equal to L over n, and it is equal to 0.2 meters, as shown in figure 210. Here, this is the base, and this is the insulated end. We choose numbering from left to the right. and if you choose the reverse direction, it will be okay for the solution. But you have to put each location with its exact with its value of the numerical solution at the end of your solution. So we start the discretization of the internal control volumes 2, 3, and this is the internal control volumes. We start the solution by predicting the algebraic equation for these control volumes. So we integrate our governing equation 240, which have a constant sink term minus HP multiplied by T minus T infinity. We call it sink because it has a negative sign. So sink for the negative and source for the positive. That means at the solution, if the temperature decreases of the domain with the increase of x, this term have to be negative. Therefore we call it sink term. If the temperature increases with the increased direction of x, this term will be positive, and it will be a source, be given a source term. So since it's negative, we will call it a sink term. The convection heat transfer coefficient, which is a function of the local temperature T, and the governing equation can be written as here as shown in figure in equation 242. Integrate this equation 242 along the control volume from west to east, and it will give us equation 243. So again, replace the dV and rearrange it, and we will then divide by the constant area A. We will have the equation 244. Rearrange it and put all the parameters, which is multiplied by Tp on the left side, and all the rest of the parameter will put it on the right side. So again, this look like this. It has to be the same shape. This is A west, this is A west, and this one the same as this one. It is A east, because here it is multiplied by A east, and this one is plus sign, therefore it is A west plus A east minus SP. Sorry, here minus SP. Therefore SP it equals to m square delta x, and this equation 245, it is when you open equation 244, open the brackets, you will end with equation 245. Therefore the parameters of this equation 245 will be given in this table, and this general discretization form of equation 245 is for the internal nodes is given in equation 246. Therefore A west equals 1 over delta x, and A east is will be given as 1 over delta x, and the same equation for calculating A point, and SP will equals, as we said, minus m square delta x, and SU, it is the last strange parameter here. It is m square delta x multiplied by T infinity. Again, we recalculate or redo the same procedure for control volume number 1, which is at the far left side of the domain, which is the boundary condition with a temperature T based, therefore there is no waste temperature. Therefore we integrate equation 242 and replace the value of T waste with a TB, and the delta X value, it will be the half the distance, because from the center of point 1 to the west side, it is half the distance. Again, if we rearrange equation 247, we will have there is no A waste value, A waste equal 0, and the same A east 1 over delta X, and A point is the same, and SP it have the value of minus m squared delta X minus 2 over delta X, and SU is m squared delta X multiplied by T infinity plus 2 over delta X multiplied by TB. This table, the parameter of this table, we can if we open the brackets of equation 247, we will definitely have the values as written in this table. For control volume number 5, which is at the far east, the gradient of temperature is 0 at the east interface. Therefore, this value which represent the gradient at the east value, it is 0 minus the gradient at the west side of control volume number 5, Tp minus T west minus T west over delta X minus the same parameter here. It will give us equation 248. Again, rearranging this equation 248 and put it in the general discretized form, it will give us this table with a value of A west 1 over delta X, and A east equal, there is no A east equals 0, and AP equals A west plus A east minus SP, and SP equals minus m squared delta X, and SU the same value as given in the internal notes. So if we assemble the three tables, we will end with the general assembly table, which is shown in this table here, and we can if we substitute all the variables within the given numbers, we will end with a 5 algebraic equation, and if we write it and in a matrix form, we will have a matrix system as shown in equation 249. As we see here, this matrix on the left, it has three diagonals, one main diagonal in the center, and there is two upper and lower neighboring diagonals. Therefore, it is called a tridiagonal matrix system, and we can solve it by the TDMA method, or using the MATLAB or our scientific calculator, and we will we hope that you have the same answer as given in equation 215. If we compare this solution with the analytical solution that is given in our example, it will lead us to a table that represents the validation of our numerical solution, and as we see here, we have a maximum error at node number 1, which is around 6.27%. And it is there is a good agreement between this solution and the analytical one. And if we increase our control volumes up to 10, we will make a refinement of our grid, and the validation of this 10 control volume solution will give us table 2, 3 with a maximum error of approximately 2.1 or 2.08%. That means when we make a refinement with level of the grid, we will definitely reduce the error value.